fast are you moving right now? If you're sitting in a chair or on a sofa watching this video, then it must be 0 speed, right? Well, not quite. If you're somewhere on the equator, you're actually moving at a speed of 1,674 kilometers an hour, which is twice the cruising speed of a passenger Boeing. This is the approximate speed at which the Earth rotates on its axis. But there's more to it than that. At the same time, you're also rushing through outer space at a speed of 30 kilometers a second. It's the average speed at which the Earth orbits the Sun. But that isn't all. 230 kilometers a second at such tremendous speed. You're right now racing through space around the center of our galaxy, the Milky Way, along with the solar system. But wait a minute, there's still more. 550 kilometers a second. That's how fast our galaxy, along with thousands of others, is moving towards the Great Attractor, a mysterious region of the universe that seems to be sucking in millions of worlds. Is there anything in the universe that moves even faster? Certainly, a lot of things. But the first thing that comes to mind is light, the fastest phenomenon in our universe. Light from the surface of the Sun reaches Earth in 8 minutes and 17 seconds. However, light is not born on the surface of the Sun, but in its core. And to escape from the core, it takes 200,000 years. That's 3.5 kilometers per year. Hold on, how is that possible? Something's clearly wrong with the speed of light. Today, you'll learn. Why is it impossible to measure the speed of light? What is the speed of light in a piece of sugar? Can light be slowed down? Why can't you move faster than light? Or can you, after all? And in general, what's wrong with the speed of light? Please like this video and subscribe to the channel for more interesting educational content on YouTube. What causes light to move in the first place? Seriously, why would it even move? When it rains, the drops move because they are pulled by gravity. This is precisely why Earth orbits the Sun. Its gravity prevents our planet from flying into deep space, and the speed of movement balances this force, resulting in rotation. When a person walks, they push off the ground with their feet, and this is precisely how the movement happens. With light, however, things aren't as simple as this. Perhaps the answers lie in the question itself. What is light, anyway? Well, the answer seems to be straightforward. Light is electromagnetic waves, and at the same time, massless particles called photons. You probably heard this at school when you were studying physics. Just in case, let us recall that electromagnetic waves include not only visible light, but also ultraviolet, X-ray and gamma radiation, as well as infrared radiation and radio waves on the other side of the spectrum. Yep, but strangely enough, radio waves and light are essentially the same thing. The only difference is in the wavelength. We can only see a very narrow segment of this spectrum, which we call visible light. This is a convention determined solely by the limitations of our sensory organs. We can't see ultraviolet, but many birds certainly can. So, there you have it, electromagnetic waves. Alright, that seems clear enough. But here's the question. Did you notice the catch? We've used the word wave several times, but never once said waves of what? Confusing. It'll all become clear soon, along with the first oddity. What is a wave? According to the simplest and very general definition, this is oscillatory movement in the physical environment. Imagine throwing a pebble into a pond on a windless day. The surface displays a distinct wave spreading out in all directions. Here the medium is water. It's easy to say that there is a wave in the water, or simply a water wave. Sound. It's also the oscillatory motion of air molecules spreading through the air, which serves as the medium for the sound wave. Or for example, by waving one end of a long rope, you create a wave that travels along it. You could say that this is a rope wave, though that sounds a bit odd. But without a doubt, the medium for the rope wave is the rope itself. This could go on forever. Wherever we find a wave, we immediately find something that it travels through, until we come to light. and electromagnetic waves in general, because it turns out there is simply no medium for electromagnetic waves. But this begs the question, if the light is waves, then waves of what? What oscillates? Through what does the wave travel? This question has puzzled scientists almost from the moment the wave nature of light was discovered. But there was still hope that such a medium existed, the luminiferous ether. They were almost certain about this. It seemed so obvious. Many scientists devoted their lives proving its existence. But this wasn't meant to be. Quite quickly, the ether story was brutally disproven. This left scientists to face a rather unpleasant reality. They had to come to terms with the fact that electromagnetic waves do not require a medium to spread. They can do this in a complete void. We could say, with a bit of a stretch, that the electromagnetic wave serves as its own medium, since in a combined wave the electric wave transitions into a magnetic wave and vice versa. They move in this way, transitioning, even transforming into one another, perpendicular to each other and the movement's direction. It can be considered a wave in itself, if you will. And this is the first oddity that suggests that something is wrong with the light. Any wave travels through something. However, light is an unusual type of wave that doesn't need this something. In other words, light doesn't need a medium to spread. Light can easily travel, even in a complete vacuum. The second oddity follows directly from the first. Let's ask ourselves a logical question. If light doesn't spread through a medium, then what determines its speed? This question is not as trivial as it might seem. After all, in all other examples, the wave's speed is determined by the medium. A wave on the surface of a pond spreads in all directions at a certain speed, which depends on the density, the nature of the intermolecular bonds, and the surface tension. The speed of the wave spreading through the air, which we call sound, also depends on the medium. On Mars, the speed of sound is approximately 240 meters per second, 787 feet per second, while on Earth it averages 340 meters per second, 1,115 feet per second. And this is because the atmosphere is different. Even a wave along a rope moves at different speeds depending on the material of the rope. But what about light? What determines the speed of light? Approximately 300,000 kilometers per second, or 186,000 miles per second. There it is, the speed of light, right? But what if we said that the speed of light is the speed not of light? What nonsense, you might exclaim. Whose speed then? This is where things get complicated, or much more interesting than they seem. The fact is, this speed is not exclusive to light and electromagnetic radiation in general. Gravitational waves and gluons move at this speed. The speed of neutrons and a whole family of particles almost reaches it. So it would be more appropriate to call the speed of light some kind of fundamental universal constant. This is literally one of the default settings of our universe. We call it the speed of light only because that's what we've gotten used to. This is because the speed of light was measured first, a long time ago, when we didn't even properly understand what light is. And only later did it turn out that this huge number is inherent to some other phenomena that have nothing to do with light, at least directly. And this is the second oddity. The speed of light doesn't depend on light and is not even related to it. It's a deeply embedded characteristic of space-time itself, on which the laws of our universe are based. Finally, let's consider the third main oddity, the most incomprehensible and even unsettling one. Even if you've heard this many times, it's worth repeating it, because most people can't wrap their heads around it. Let's keep this approximate figure in mind. 300,000 kilometers per second, or 186,000 miles per second. No more, no less. Always, everywhere. Let's say you're flying on a starship at almost this huge speed. standing on the captain's bridge. You turn on a flashlight and direct the beam forward along the course. At what speed will the beam ultimately travel? Logic suggests that you should add the speed of the beam to the speed of the starship. After all, if you're driving a car and throw a ball forward, the speed of the ball equals the sum of the speed of your car and the speed at which you will throw the ball. But logic doesn't work here. The speed of the flashlight beam will still be equal to that same stubborn figure, 300,000 kilometers per second or 186,000 miles per second. No more and no less, always everywhere. It's quite hard imagining this, but let's stretch our point here and illustrate this with a very rough example. Imagine that you're slowly walking through a large but very shallow puddle. With every step, each plunge of your boot sends water ripples in all directions at the same speed. You can walk faster or slower, but the speed at which each wave spreads will always be the same. Or take the speed of sound, for example. The source of the sound can move at any speed, whether it's the sound of a flying jet or the roar of an erupting volcano standing still. The speed of sound does not add up to the speed of the object emitting it. Once again, these are very rough, oversimplified examples, because the constancy of the speed of light is absolute. It doesn't depend on anything, it just is. And this is the third most disconcerting oddity. The speed of light is always constant and never changes. In all inertial frames of reference, it remains constant regardless of the speed of the source or the observer. This phenomenon is counterintuitive and truly baffling, but it has been confirmed by numerous experiments and is one of the fundamental principles of modern physics. However, scientists realized this only centuries after this speed was measured. An attentive viewer might say, hang on, what do you mean by centuries after? Was the speed of light measured hundreds of years ago? But how? What kind of medieval technology would have allowed us to do it? After all, it's not hard to figure out that at such speed, light can circle the globe at the equator 7 times in 1 second, provided it could move in a circle. Now, what kind of devices must those people have had to be able to do this? Mind you, the steam engine hadn't been around back then, let alone a collider. In fact, the most primitive devices and ingenuity, remarkable intelligence, and curiosity took care of the rest. Think of how you would measure the speed of light if you were really motivated to do it. Surely, you would agree with a friend to climb to the tops of neighboring mountains, where you would turn flashlights on and off and record the time. The algorithm seems pretty straightforward. 1. You turn on the flashlight and note the time. 2. Your friend on the neighboring mountain also records the time when he sees the light from your flashlight. 3. Then you both compare the time readings to see the difference. 4. Divide the distance between the peaks by this difference. 5. Presto. We get the speed of light, right? This is exactly what Galileo Galilei thought. And that's exactly how he tried to measure the speed of light in practice. Galileo and his assistant climbed the hills with lanterns, knowing the precise distance between them. One of them would open the shutter on the lantern and the other was supposed to do the same when he saw the light from the first lantern. Knowing the distance and the time delay before the assistant opened his lantern, Galileo planned to calculate the speed of light. However, it didn't work out. The time interval turned out to be so short that Galileo almost equated it to be the human reaction speed. He concluded that the speed of light must be too fast to be measured by the tools and methods available at that time. Nevertheless, this was still progress. After all, most ancient scientists were convinced that light moved instantly. However, Galileo's findings suggested that the speed of light was finite. And in the 17th century, the distinguished Danish astronomer and mathematician Ole Rømer conclusively proved this. The scientist was then working at the Royal Observatory in Paris. He made his first measurements by observing the eclipses of Io, one of Jupiter's moons. Let's clarify what we mean by an eclipse here. The sun has nothing to do with it. We're talking about the part of Io's orbit when the moon disappears behind Jupiter, as seen from Earth. This is why we don't see it for some time. which is what we call an eclipse. Römer, like other astronomers of his time, was well aware of the oddity associated with this eclipse. Here's the thing. The moon Io orbits Jupiter in a very stable and predictable manner, just like the Earth orbits the Sun. We know very well that the Earth's orbital period is exactly 1 year. Even in ancient times, this knowledge was used to calculate the seasons and, therefore, to make future plans. Similarly, with other celestial bodies, including Jupiter and its moon, you can easily calculate where the moon will be at any given time, even hundreds of years in advance. But here's the problem. Astronomers noticed that the eclipses of Io sometimes started later than they thought, depending on the time of the year. Io orbits very rapidly around Jupiter, completing a full orbit in just 42 hours. So astronomers didn't have to wait long to compare readings and calculate this discrepancy. Therefore, observations were conducted frequently, and each one only confirmed this strange and inexplicable delay. Take a look here. The Earth orbits around the Sun and at a certain point is at its closest to Jupiter. An astronomer looks at his watch. It shows midnight. He looks through the telescope towards Jupiter and observes the moon Io begins to disappear behind Jupiter. 42 hours later, Io, having completed a full orbit around Jupiter, appears in the same place again. Everything is obvious and predictable. Now imagine that exactly 6 months later, the same astronomer from the same place on Earth wanted to observe Io hiding behind Jupiter again. He easily calculated the time of day when he needed to sit down at the telescope. The observation begins and, according to calculations, Io should be visibly touching Jupiter right now, going behind it like this. But the astronomer discovers that the moon is still on its way, so it looks more like this. And the eclipse will start only a whole 22 minutes later. But why is that? Why was there an error in the calculations? No, everything has been checked many times. There can be no mistake. Has Io begun to orbit Jupiter more slowly? Of course not. It's also easy to check. So what happened? Many astronomers noticed this discrepancy, but for a long time, no one really understood its cause. They couldn't all be wrong. And they weren't. They simply didn't realize that it wasn't about Io or even Jupiter. It was about the speed of light. And it was Römer who figured out to link this discrepancy with the distance from Earth to the Jupiter system. The fact is that Earth also orbits the Sun and thus becomes closer or further from Jupiter depending on the time of the year. In 1676, Römer once again observed Io through a telescope and discovered that the time of the moon's eclipse shifted slightly compared to the calculations as the Earth moved away from Jupiter. At some point, this delay reaches a maximum of 1,320 seconds. That is a whole 22 minutes. Clearly, this was something much more serious than just a discrepancy. Römer realized that the maximum eclipse delay occurs when the Earth is at its furthest from the Sun. That is, when the distance between our planet and Jupiter is maximum. And at some point, it dawned on him. The scientist suggested that this delay is the time that light needs to travel the additional distance. From the nearest position of Earth to Jupiter in Earth's orbit to the farthest. The differences between them equals the diameter of the Earth's orbit around the Sun. Let's see how this happens. Imagine yourself in Römer's place. Here is Io's orbit around Jupiter, and here is Earth's orbit around the Sun. At a certain time of year, Earth is here, as close as possible to Jupiter and Io. Another eclipse of Io begins. We observed it and recorded the time. And now, 6 months later, Earth is at the opposite end of its orbit around the Sun, meaning it's maximally far from Jupiter. We'd like to repeat the observation, calculate the time and sit down at the telescope, but the eclipse of Io begins 1,320 seconds, or 22 minutes later than it should, because the light simply needs to travel the extra distance. We don't know for certain whether Römer continued his train of thought and solved the riddle of the speed of light. Most of his work was destroyed during a fire in Copenhagen in 1728. and it's unknown whether he announced the discovery of the speed of light. But he proved that it has limits and determined them. Using modern knowledge of the celestial body's orbits, we can calculate that Romer's experiment would have shown the speed of light to be 226,663 kilometers a second. This is almost a quarter less than the true value. Romer was noticeably mistaken, as at that time the diameter of the Earth's orbit and the time delay of Io's eclipse were measured inaccurately. Nonetheless, this was another important step forward. 50 years later, in 1728, thanks to the discovery and the phenomenon of a light aberration, the English astronomer James Bradley refined this figure to 308,000 kilometers a second. Although this figure was a bit too high, it was very close. Later, the speed of light was measured by French astrophysicists François Arago and Léon Fourceau, who obtained a result of 298,000 kilometers a second. Then there was Michelson's experiment, which brought us even closer to the correct figure. Scientists finally settled on a value in the second half of the 20th century when masers and lasers were developed, distinguished by their extremely stable frequency of radiation. By the early 1970s, the error in measurements had decreased to 1 kilometer a second. As a result, the 15th General Conference on Weights and Measures, held in 1975, decided to consider the speed of light in a vacuum henceforth to be 299,792,458 meters a second. It looks like we have everything figured out, right? Now, get ready for something unexpected. The fact is that the speed of light has never actually been measured. No, we're not trying to stir up cheap intrigue or conspiracy. All these experiments were actually conducted in ancient times, but we can't say that they conclusively measured the speed of light. Moreover, the same holds true even for the most modern measurement methods. You might say that's not even funny. There's definitely some kind of catch here. And you'd be partly right, but only partly. In fact, sometimes reality is more amazing than any fantasy and even more elusive than a dream. Let's go step by step. How do we measure the speed of ordinary objects? For example, how would you measure the speed of a baseball shot from a cannon? For this, we need two things. First, the distance between the 2 points, and second, the time it takes for the ball to travel from one to the other. Then we simply take the distance, divide it by the time, and that's how we get the speed. Plus, we have high-speed cameras at our disposal. We can count the frames and correlate them with the built-in camera timer. No problem, so why can't we measure the speed of light in the same way? After all, it would seem that even our great ancestors did this repeatedly hundreds of years ago. Alright, let's imagine we have a laser that fires a beam through a perfect vacuum over a distance of 1 mile. We start the timer when the laser is turned on and stop it as soon as the light passes that 1 mile. But how do we know when the light reaches the end point if the timer is on and we are at the starting point? Apparently, we need 2 timers for that, one at the laser and one at the end of the path. We'll start them simultaneously, and the second timer will stop the moment it detects the arriving beam. But first we need to synchronize the timers, otherwise the measurement results will be useless. How to synchronize them? We could throw a wire to transmit the signal from one timer to the other over a distance of 1 mile. However, the signal won't reach the other side instantly, but will travel through the wire at the speed of the light and reach the second device with a delay. In case you didn't know, electric current also travels through wires at the speed of light. Perhaps we could subtract the delay, but that's exactly the time it takes for the light to travel 1 mile in one direction, and that's exactly what we don't know and are trying to measure. Okay, well, let's try a different approach. We'll connect the 2 timers, synchronize them, and then move the second timer to the end point 1 mile away. What could possibly go wrong? Well, everything. After the synchronization, we'll move the second clock relative to the first one, which will remain stationary. According to the special theory of relativity, time flows slower for the second clock than the first, based on the stationary observer's perspective. So when the second timer reaches the right place, it'll already be out of sync with the first one. Of course, the difference may be very slight, but we will definitely be there, and there is no way to avoid it. What the hell? Okay, let's throw away the second timer, put a mirror at the end of the path. That would reflect the light and use a single timer to measure the time that it takes for the beam to travel 2 kilometers there and back. Does this remind you of anything? That's right. That's exactly what Galileo and his followers tried to do. We've come full circle. This result isn't valid because we didn't measure, but calculated the speed of light, based on indirect evidence. But has anyone measured the speed of light directly or not? No. In fact, what was measured was the path of light in both directions there and back. But no one has ever measured the one-way path. It might not seem like a big deal, right? Could the speed of light in the opposite direction possibly be any different? Come on. But why not? What if light really flies at one speed in one direction and at another speed in the other? Now, try now to keep an open mind, even if this idea sounds naive and stupid. It's questions like these that were a stepping stone into making groundbreaking theories that have fundamentally changed our lives. Let's imagine how we would communicate with astronauts on the nearest planet, Mars. The distance varies significantly throughout the year, so for the sake of simplicity, let's take the position where the light from the Earth takes 10 minutes to reach the red planet when the light reaches it from the Earth in 10 minutes. We send a signal and receive a response after 20 minutes. Thus, we assume that the signal reaches Mars in 10 minutes and takes the same time for the response to come back. But is there a real basis for this assumption? What if the signal takes the full 20 minutes to reach Mars and the return signal arrives instantly? After all, both scenarios would work the same for us and we wouldn't notice the difference. What if some directions in space are more favorable to light than others, if you will? It sounds absurd at first glance, but only at first glance. After all, there are plenty of things and phenomena in the universe that should be symmetrical but aren't in reality. For example, the imbalance in the content of matter and antimatter. Not to mention dark matter and energy. There are even extravagant but entirely consistent theories where the speeds of light to and from a point could be different. At least such scientists as Professor Geraint F. Lewis from the University of Sydney and Dr. Luke A. Barnes from Western Sydney University are courageous enough to have a serious discussion about it. The difference can only be a couple of %, but what if light travels in one direction twice as slowly as we thought but comes back instantly? This still sounds incredible because, let's face it, it's hard to accept that there is such a gaping hole in our scientific understanding of the world. If Einstein were alive, he'd probably ridicule such assumptions. Or not. Well, actually, no. Because it was Einstein who paid attention to this problem. The great scientist understood better than anyone else that this problem exists. He emphasized it in his famous 1905 paper on the electrodynamics of moving bodies. In the very first pages, he discusses the problem of synchronizing clocks at point A and B. Einstein explicitly writes that without additional assumptions, it's impossible to compare the times of events unless one introduces a definition that the time required for light to travel from A to B is equal to the time required to travel from B to A. In fact, he artificially equated the speed of light in one direction to the speed of light in the opposite direction. He even italicized it in his book, saying established by definition to remind us that this is merely a convention. Scientists later called this Einstein's synchronization. Thus, he would write later that the notion that the speed of light is the same in both directions is not a premise or a hypothesis about the physical nature of light. It is merely a requirement introduced to define simultaneity. You see, Einstein already understood that there is no way to accurately measure the speed of light in one direction, only in both directions, and then calculate the average. But as you'd agree, it's not the same thing. For more than 100 years, scientists have been looking for a way to get around this problem and measure the speed of light in one direction. In 2009, a paper was even published in an American scientific journal whose authors claimed they had succeeded. But another scientist quickly refuted this, proving that they'd actually measured the same average speed back and forth, but in a more intricate way. Are there still ideas on how to measure the actual speed of light in one direction? Maybe just turn on a high-speed camera that takes trillions of frames per second and see how light passes through a transparent object. However, this method simply won't capture anything because the light can't be seen from the side, only if it flies into the camera lens. Those bright laser beams that we see from the side are also essentially light reflected off air molecules. In a vacuum, there'd be no beams to see from the side. But what if you place a synchronizing device between two clocks, which send the synchronization signal simultaneously in both directions? If the speed of light is the same in both directions, then our task is solved. But if not, then the synchronizing signals will reach the clocks at different times. After all, the signal will fly along the wire in the opposite directions, that is, at different speeds. This means that one clock will be running faster than the second one from the very beginning, by such a value that when we finally measure the speed of light, it will turn out to be exactly what we know it to be, almost 300,000 kilometers a second, even though this may not actually be the case. This is how you can dodge and come up with method after method ad infinitum. Actually, scientists have been doing this for 100 years. They haven't come up with anything. It turns out that we are at a dead end. To measure the speed of light in one direction, we need to synchronize the timers. But in order to synchronize them, you need to know the speed of light in one direction. We return again to the fact that in the physical world there seems to be nothing more elusive than light. Not only elusive, but also irresistible. All or almost of you have heard many times that one cannot surpass the speed of light. We'll come back to this vexing cosmic injustice later, but for now, let's remember that according to modern physics, space and time are inseparably linked, like north and south, east and west. After all, the south cannot exist without the north, so time cannot exist without space in our world. Even more, it is essentially one entity, and this entity even has a simple and straightforward name: space-time. What does this connection and strange configuration imply? Well, some very amazing stuff. For example, how fast do you think a stationary object moves in space-time? Do you think the answer is zero speed? If this question seems stupid, take your time, because the actual answer might sound absurd. Any object moves in space-time at the speed of light, even motionless ones. This may come as a surprise to you, but there's nothing inherently paradoxical or even absurd to it. Because if you were paying attention, you'd notice that we're not talking about space, but about space-time. And any object with zero speed in space is actually still moving. It's just moving in time, always. It can't help but do this, because the so-called arrow of time always inexorably points forward, and it always moves at the speed of light. But in time, not in space. This sounds somewhat nonsensical, like 1 second per second. It's like saying I walk 1 mile per mile. But essentially, that's exactly how it is. Yes, from a physical point of view, this is indeed a movement no matter how hard it might be to comprehend. By the way, have you ever found it strange that we use the same words for positions in time as we do for positions in space? Back to the past. Look into the future. Time flies, etc. Think about this in your spare time. Well, let's move on. How does this benefit our understanding? Look at the map of the world. We can determine a location on a map in terms of two numbers, latitude and longitude. With space-time, it's almost the same. We all move forward through time or space, just as a traveller moves east, west, or north, south. To make this easy to understand, let's imagine that you're in a large flat area, for example, in the Bonneville Salt Flats in Utah, where racers gather every year. You're getting into a car with a locked accelerator, so it can only travel at one speed, 100 kilometers an hour. This will be our conditional model of the speed of light limitation. We'll show everything that happens from above and present in a chart. The x-axis shows the way to the east, and the y-axis the way to the north. You start the engine and drive off. If you drive strictly east for 60 miles per hour, you're not moving at all in the north-south direction. Similarly, you could drive north at the same speed, but then you would not be moving east or west at all. And if you drive northeast at 60 miles an hour, you'll be moving partly north and partly east, and your speed would be distributed between these directions. Accelerating towards the north, you automatically slow down towards the east and vice versa. Finally, if you drive north at maximum speed, your eastward speed becomes zero and vice versa. Now replace the word north with time and east with space in this thought experiment. Please look at the diagram. If you move through space at a maximum speed, the speed of light, then you won't move through time at all. It would kind of stop you. And even after moving over vast distances of billions of light years, you won't feel the passage of time. This would feel like one moment for you. On the other hand, there's no way for you to stand still, because time moves inexorably forward. In fact, it turns out that everything in the space-time always moves at the speed of light. It's just that one part of this speed falls on the north, time, and the other part on the east, space. That is, you're never simply standing still in space-time. You move either at some speed in space or in time. If the speed in space increases, then the speed in time decreases, and vice versa. Like in this diagram where the vertical represents the speed of time and the horizontal is the speed in space. Take a look here. When we increase the speed in space, time slows down. When we decrease the speed in space, time speeds up. That's how the space-time continuum works in simple terms. To complete the picture, let's look at all these amazing effects through the eyes of the person who figured them out. For a moment, imagine yourself as Einstein. While still a young clerk at a patent office in Bern, Switzerland, Albert Einstein had a sudden insight. One evening in May 1905, he heard the chimes of this old clock tower. All of a sudden, he was struck by a wild idea. What if the tram rushed away from the tower at the speed of light? And then he realized that if he looked back, he would see the tower clock had stopped, along with everything else: pedestrians, birds in flight, raindrops. This is because we see everything only thanks to the light that reaches our eyes. And if we were to move at the speed of light, then new reflected beams of light simply wouldn't be able to catch up with us, and we would only see that last frozen time. Note that the light would continue to move at the same speed, though it seems as if everything has frozen, even the light itself. After all, light cannot just stand still. It cannot even slow down. Not at all. Now we'll respond to the argument that the speed of light is only maximal in a vacuum and drops in other media. Indeed, this is the speed of light in water, and this lower value is in glass. This might sound amusing, but enthusiasts even calculated the speed of light in sugar. Here it is. But here we are talking about media that have what is called a light refraction index. If we send a laser beam through such a medium, light will interact with this material. Atoms of the material absorb photons of light and re-emit them. But when we pass light through a transparent medium, we don't slow down the photons. We are, roughly speaking, destroying them and then sending their descendants to continue their journey. This is just one very simplified interpretation of this phenomenon, because this process involves polarization effects and much more. But that is not the topic of our video. This is only one conclusion. Light cannot move slower than the speed of light, nor can it move faster. If you remove the matter and leave only an empty vacuum, then everything will go back to normal. You can neither slow down the light nor speed it up. No way at all. You wouldn't be able to fly faster than light too. And there are a number of reasons for this, which are as relentless as fate itself. As the speed increases, so does mass. And as you approach the speed of light, it grows exponentially and to infinity. Consequently, an infinite amount of energy is needed to reach the speed of light. You can burn all the stars of the universe in the furnace of such an engine, but you still won't be able to reach the speed of light, let alone surpass it. This is just one of the reasons. Another one is time dilation. And then there are violations of causality. You've probably heard all of this many times. There's one more example, but for some reason people rarely discuss it. If you decide to fly faster than the speed of light, you'll face another insurmountable problem. Electromagnetic interactions in your body also occur at the speed of light. It turns out that to move faster than the speed of light, you would have to move faster than yourself. This, of course, is an extremely illustrative example, but it's still close to how things actually are. So no, unfortunately, there is no way. But who says we can't dream or imagine? After all, we can at least imagine what would happen if we flew at the speed close to the speed of light, or equal to it, or even faster. What would we see from the window of such a fantastic starship? Can we imagine? Of course we can. And we'll even show it to you. Get ready, there's going to be some action. Imagine that you're an astronaut in a super powerful spaceship. It can go almost as fast as light. In terms of speed of light percentage, you can put any number of 9s in this value. For the sake of simplicity, let's assume that the ship accelerates and decelerates instantly. How long do you think it would take, from the crew's perspective, to travel at almost light speed to the nearest star? Proxima Centauri, located 4.24 light years away from us. It's logical to assume it would be just over 4.24 years, right? Well, no, not even close, and you'll be very surprised to learn the actual answer. So let's say our starting point is Earth and our endpoint is the already mentioned Proxima Centauri. It takes light 4.24 years to reach it from Earth, and we will take exactly the same journey. No, you won't have to sit in front of a monitor for 4 years, just a minute of patience. Let's skip all the usual concerns, fuel capacity, engine power, human frailty, and the like. Let's assume we've somehow successfully solved these issues. In fact, we've been so successful that we can even travel in 2 different ways. Instantly reaching the speed of light, or quickly but gradually accelerating to the speed of light and decelerating at the end of the journey. In terms of the pilot's experience sitting inside the spaceship, these options will differ drastically, and sometimes even counterintuitively. You'll see completely different things. So in the first option, we'll reach the speed of light instantly, as soon as we start. Get ready. 3, 2, 1, go. That's it. We've arrived. Here is Proxima Centauri, a red dwarf star in the triple star system, Alpha Centauri, the closest star to the Sun. No, this is not a joke or a sped-up demonstration. This is exactly how you, as the pilot, will perceive this flight. As an instant movement, not even movement, but more of a teleportation. Because you won't even notice the process of flying in space or its duration, neither visually nor in terms of time. Everything will happen instantly. As an attentive viewer, well versed in physics, you might say, hold on, but you yourself said it takes light 4.24 years to reach Proxima Centauri. If we are flying at the speed of light, how could we arrive there instantly? In fact, there is no contradiction. For a hypothetical dispatcher at NASA's Space Center in Houston, your journey will indeed last those 4+ years. But for you, it will be an instant. This is because in this thought experiment, the effects of the theory of relativity are not just observable, they're taken to the max. Remember, the higher the speed, the slower time flows, for the one moving at that speed. Hold on, something is wrong again. If, as a pilot, I would experience a maximally slowed down time, then how come I would arrive at Proxima Centauri in an instant? It should be the other way around. That's right, in the cockpit everything will actually stop during such a flight. But from the perspective of an external observer on Earth, not from the pilot's perspective. Relatively, everything is relative. Keep this word in mind always when thinking about near light speeds. Better yet, never forget about it. Let's move on. So, we understand instant acceleration now, and frankly, it's quite boring. What would happen if our spaceship were to gradually accelerate to the speed of light? Let it be very fast, but still gradual. Oh, then there'll be bright special effects. They'll be literally bright, and soon you'll understand and even see everything. You might expect to see a scene similar to what we all know from Star Wars. In fact, things will get no less interesting, and even more so. It'll look something like this. 3, 2, 1, go. That's it, we're here. Yes, this is definitely more interesting than the instant acceleration, but this immediately raises questions. Why do we initially seem to fly backward? And what about that blinding flash in the middle of the journey? Well, let's find out. The first thing that strikes your eye is the unusual distortion of space. The field of view seems to expand as if we were filming with an action camera. This makes us feel like we're moving backward. This occurs due to light aberration, a change in the direction of rays of light due to movement. A simple example is a car in the rain. When the car is stationary, the drops fall straight from above, but when it moves, the drops seem to fall at an angle. At very high speeds, it would appear that the rain is coming right at you. If the speed of light were equal to the speed of raindrops, then not only would you feel the drops flying horizontally right at you and not from above, but you would also see thunderclouds not from above, but right in front of you. For the same reason, everything ahead seems brighter, just as a car's windshield at high speed collects more drops as it moves forward. So the viewpoint of our starship will collect more photons and space will appear brighter. Alright then, if we could imagine such an impossible situation as flying at the speed of light, then perhaps we can imagine what would happen if we exceeded it. At least just imagine. Unfortunately, no. This is a meaningless question if discussed in terms of visualization. Even a photon cannot travel faster than the speed of light because a photon is light. This is the same as asking what would happen if light moved faster than itself. It's not even a paradox, it's just nonsense. But here, the romantics and optimists of interstellar travel will put forth a final yet very compelling argument. There are two methods we know of that can serve as a loophole to the speed limit of light limitation. Modern physics doesn't contradict and even occasionally proves the existence of wormholes. These are formations that directly connect distant areas of space, bypassing space itself. This concept was thoroughly explored in the film Interstellar. The idea of wormholes was first proposed by Einstein and his colleague Nathan Rosen in 1935. They suggested that within the framework of the general theory of relativity, black holes could be connected by bridges that function as portals. This later came to be known as the Einstein-Rosen bridge. But the further development of theoretical physics expanded the potential possibilities even more. It turned out that you don't need to travel to a black hole to find a wormhole. Such formations could definitely form anywhere in space, but on an ultra-small scale, much smaller than the size of an atom. All that remains is to capture, expand and stabilize such a wormhole. How would it work in practice? A popular example involves taking a map of the USA, where an ant crawls from New York to California, which would normally be a long journey. But let's fold the map so that the two opposite ends, New York and California, touch each other. Now punch a hole in New York with a pencil, and there we have it, a wormhole. The ant will only need to take a couple of steps into this hole to come out on the opposite side where California is. It works much the same way with space, only in this case, we would connect two distant areas of space. Of course, we're not talking about literally folding the entire cosmos, as in the example with the map and the ant. It's just that this is the clearest example we can visualize. But there's more to it than wormholes. Until recently, faster-than-light warp drives were only the province of scientific and not-so-scientific fiction. That was until theoretical physicist Miguel Alcubierre proposed an unexpectedly bold but coherent theory in 1994, and even NASA took an interest in it. We discussed this in detail in one of our previous videos. Let's briefly recap what we are talking about. Alcubierre found a solution to the gravitational field equations of Einstein's general theory of relativity, which allows for the deformation of space. For this, you need to make a tremendous effort to create a very complex engine, but at least this doesn't violate the physics as we know it. How does it work? Look, here's a spaceship with that very super engine capable of bending space. So we turn it on and gradually increase the power. Space expands in front of the spaceship and at the same moment in time contracts behind it. Thus, the ship enters a bending bubble, which has come to be called the Alcubierre bubble. Thus, the movement occurs due to this difference in the conditional density of space. But the trick is that the starship is stationary within this bubble of distortion. It's the bubble itself that moves. Thus, the laws of general relativity are not violated. After all, only the distortion bubble moves, which locally deforms the space-time continuum. Once again, this isn't fiction or science, but a coherent and recognized theory. But there's just one caveat. We need very exotic things to bend space like this. For example, negative mass. Where and how do we get it, and whether it's even possible, is something scientists still need to figure out. But human history has shown us many times that we're capable of incredible things. New generations have repeatedly overcome what previous generations considered to be laws of physics. This is how we could theoretically cover distances of over hundreds or even thousands of light years in a matter of hours or even minutes. And such travel wouldn't violate the speed of light limitation because it isn't movement in the sense of the word. So it turns out there's hope after all. Will we eventually be able to quickly overcome interstellar distances? So theoretically speaking, is there a chance? There is, but there's also one unpleasant problem. It's called casualty violation. The speed of light isn't just about the speed of movement, but about the speed of transmitting any kind of information. That is, in brief and simple terms, we have no way of knowing what Proxima Centauri looks like at this second. We'll only find out more than 4 years from now, when the light it emits this very second finally reaches us. Now imagine that we have a wormhole between Earth and Proxima Centauri. We would dive into the wormhole, emerge on the other side, take a picture of the star and come back. Bingo! We've obtained information about the star before its light reached us. Science doesn't yet know how to handle this. This is a paradox. A problem with no solution. At least for now.